Good afternoon, class. Today we'll be talking about our second semester of geometry. And what we're looking at today will be mainly fractions, ratios, proportions, and geometric means. So let's start right away. Concept 1. Concept 1, ratios. It's two numbers that can be compared, and one of the numbers cannot be 0. A ratio is two numbers that can be compared, such as A to B here. That is two numbers I can compare. The only thing that can't happen is this can't be 0. If it's 0, this ratio does not work. As long as B isn't 0 though, it works. I could do 0 to 5, fine ratio. I could do 1 to 3, 7 to 4. All these are perfectly fine as ratios. The one I cannot do though is 1 to 0, 2 to 0. These don't work. And there's three ways to write them. You can write them the way I wrote it. You can literally write out ratio of 1 to 2, ratio of 0 to 5, ratio of 1 to 3. Or you can write it as a fraction. The first number goes on top, the second number goes on bottom. So for instance, down here, if I was asked to compare this equilateral triangle to this equilateral triangle, I would say it would have to a 2 to 3 ratio. Because this side is 2, this one is 3. I'm comparing two numbers, 2 to 3. Alright, the next thing that we need to know about ratios is they can be simplified. Sometimes we get these really bulky ratios, and I don't want to know what 105 to 85 is. I'd rather get it in simplest terms. I want it as simple and concise as possible. So ratios can be simplified. If all parts of the ratio are a multiple of the same number, then you can divide all the parts of the ratio by that number. Quick example. So, if I have 8 to 16 here, I could also write it this way, 8 to 16. Either way works. Well, 8 is a multiple of 8. 16 is a multiple of 8. If I divide this number and this number both by 8, I get 1. 8 divided by 8 is 1. 16 divided by 8 is 2. This ratio of 1 to 2 works. Same thing over here, it's 1 to 2. That was the first example. Mainly you will see me write it as this way or this way. Sometimes I will write it out fully as ratio of blank to blank. But most of the time you'll see me say ratio of 1 to 2, ratio of 1 to 2. 6 to 18. With 6 to 18, I see they're both even. So let's try 2. 2 goes into 6 3 times. 2 goes into 18 9 times. Alright, they're both not even. 2 is out. Oh, but 1 is 3 and 1 is 9. Let's try 3. And there we go. Again, in the next example, you can say, alright, 8 to 10, they're both even, so they should both be a multiple of 2. Therefore, 8 divided by 2 is 4. 10 divided by 2 is 5. That ratio can be written as 4 to 5. Any ratios that can be simplified to the same one is what we call equivalent ratios. These two ratios are equivalent. These two ratios here are equivalent because they both can be simplified down to 1/2. 3 divided by 3 is 1. 3 divided by 6 divided by 3 is 2. 4 divided by 4 is 1. 8 divided by 4 is 2. They both have the same simplified verb form. So 3/6 and 4/8 are both the same ratio essentially. But because they aren't exactly the same, we call them equivalent, basically meaning of the same value. Alright, example 1. Find the ratio of the base to the height of each triangle. Simplify the ratio if possible. Forgive me for the quick sketches. For each of these, they want me to find the ratio of the base to the height. Well, the base here will be the bottom of my triangle. The height is the altitude from the vertex to the side as a right angle. So base to height, well, it's 15 to 10. Well, both of those are a multiple of 5. They both end with a 5 or a 0. So divide both sides by 5. Divide both parts by 5. You get 3 and 2. I can't simplify those any further because they're both prime numbers. Over here, base is 5, height is 7, 5 is prime, 7 is prime. You can't do anything with that. My ratio is 5 to 7. And last but not least down here, 20 is my base, 30 is my height. Both of those end with a 0. They're both multiples of 10. Divide 20 by 10, I get 2. Divide 30 by 10, I get 3. So this ratio is a 2 to 3 ratio. This is a 3 to 2 ratio, and that's a 5 to 7 ratio for base to height. And that's all this question is asking. I'm done. They didn't ask me to find an unknown length. They didn't ask me to find area. They just said find the ratio, simplify. Perfect. All right, next example. What if I gave you something a little bit tougher? I said, all right, I know 3 variables. They have values of 5, 9, and 15, respectively. X is 5, Y is 9, Z is 15. Okay, write the ratio in simplest form. So now I'm giving you a few different types of ratios, and what I want you to do is plug in the number. All right, and these are what I have. So now the next part, I plug in the number that I'm given for each of these. I know X is 5, Y is 9, and Z is 15. So in the first problem here, I just plug in 5 for X, I plug in 15 for Z, and I first of all just make it so I get 2 whole numbers in a ratio. So this is 5 to 30. Okay, now that I have 2 numbers, 5 to 30, I'm going to try and simplify it as far as I can possibly take it. Well, they both end in a 5 or a 0, so that means both are divisible by 5. It goes evenly into both of them. 5 divided by 5 is 1. 30 divided by 5 is 6. So this ratio is 1 to 6. I've put the ratio in simplest form. When you get 1 to something or something to 1, you're done automatically, assuming you did everything correctly. The next problem, again, plug in what you know. 9 for Y, plus 3 stays the same, and Z is 15. Well, make it 2 numbers in a ratio. 9 plus 3 is 12, 15 is 15, I have 12 to 15. Now that I have a number to a number, how can I simplify this further? Well, 3 goes into both of them. 12 divided by 3 is 4. 15 divided by 3 is 5. 5's prime and doesn't go into 4. I'm done. Note how I'm working here. I'm working straight down. There's no equal sign. These things here are called expressions. You cannot put equal signs with these. If you work across sideways, you should be using arrows to say this is what's next. If you are working straight across, use arrows, not equal signs. It's not an equation. The last one here, x times y. Well, x is 5, y is 9, so plug it in. Z is 15, and I have to square it. 5 times 9 is 45. 15 squared is 225. If I had to take a random guess here, they both end in a 5. Let's divide the top and bottom by 5. 45 divided by 5 is 9. 225 divided by 5. Oh, both are divisible by 3. In fact, 45 is also divisible by 5. 45. It's the 5th one. So 9 times 5 would be 45. So let's divide both the top and bottom by 9. 9 divided by 9 is 1. 45 divided by 9 is 5. My ratio here is 1/5. Done. This is what I'll be asking for if I'm just asking to do the ratio, simplify it. I'm basically saying get it in its simplest form and make sure that you have a number to a number at the very end. Sometimes you'll have x's or y's or variables in this, but for the early part of this chapter, you will only have to worry about basically number to number, at least for now. Alright, in example 3, we've come across our first case of what we call an extended ratio. Sometimes when we compare 2 numbers, we're actually sometimes comparing 3. The reason why is maybe I'm comparing all the angles of a triangle. Maybe I'm comparing all the sides of a quadrilateral. Maybe I'm comparing all the angles of a pentagon. These extended ratios sometimes go to more than one shape or more than one pair of numbers. So in this example here, when they say it here, it says the measures of the angles of the triangle have the extended ratio of 2x to 3x to 4x. Well, what that's saying is, in this triangle, I'm going to change this ratio. I know on the problem it said 2x to 3x to 4x. Instead, I want to do 3 to 4 to 5. That's the extended ratio of the angles of this triangle. Now, if I think what that's saying is, if I compare these three angles, this one's 3 to 4, this one's 4 to 5, and this one's 3 to 5. So it's just extending the pair, so it's 3 to 4 to 5. Now, if I use what I know from last chapter, 3, 4, and 5 add up to be 12, and that's nowhere near 180 degrees. But this ratio has to be true. It has to be 3 to 4 to 5. But it doesn't have to be the simplified form of 3 to 4 to 5. It could be a multiple. So if it's a multiple, that means it could be 3x to 4x to 5x. This is why I wanted to change the problem. I had actually made it too easy in the extended ratio part because I already gave you that it's a multiple. Sometimes they say it's 3 to 4 to 5, and they don't tell you it's a multiple. So you have to come in and put the x's by yourself. At this point, I now use the rule I know from before. The three angles of a triangle have to add up to be 180. That's true, always. So I look, I have one variable, x. Solve for it. Combine like terms. 3x plus 4x plus 5x is 12x. 180 is 180. And if I'm trying to solve for x, I divide both sides by 12 here. X is 115. Now, I found x. But that's not what I was looking for. It asked me, what is the measure of the angles? Well, the measure of each angle would be if I take this 15 and plug it back in. So, one of my angles is 3 times 15, or 45 degrees. Another one of my angles is 4 times 15, or 60 degrees. And my last angle will be 5 times 15, or 75 degrees. Those are the three angles of my triangle. And they do have the ratio of 3 to 4 to 5. And that's where I got away with putting 3x to 4x to 5x when I was only total was 3 to 4 to 5. So, extended ratios isn't much different than a normal ratio. We just use it to apply something that we learned last chapter, that all the angles of a triangle add up to 180. Lucky for you, we don't stop at ratios. We go to proportions. Proportions, this is where we get away from that expression. I know in the last example problem 2, I said stay away from using an equal sign. We don't use that yet. Please don't use equal signs until we deal with proportions. An equation that states two ratios are equal is called a proportion. If you make a ratio into a proportion, you have lied. You have made something wrong. Unless you're using it to solve a problem. Alright, so I give you an example of a proportion. A to B equals C to D. That's a proportion. The means, this is what we name the parts of it, so I can talk about the parts and give you a property real simple, or real quickly. The means of the proportion are B and C. Well, that means the bottom left, upper right is what I call the means of my proportion. The extremes are A and D. A and D are the extremes of my proportion, the upper left and bottom right. So if I look at my example on the slide, 5 to 6 and 18 to x. 5 and x are what we call the extremes because of where they're located, upper left, bottom right. 6 and 18 are called the means. Now, the entire reason I need you to know this is because when we talk about the geometric mean, or if I'm talking about the cross product property, or other such properties or devices that we use, we sometimes refer to just the means or just the extremes of a proportion. You need to know what I'm talking about if I said, hey, the means of the proportions are multiplied and it equals the extremes of the proportion multiplied. Okay? The other part of proportions you need to know is the proportion property called cross product property. To solve a proportion, we can use this property. In a proportion, the product of the means equal the product of the extremes. So this was my ratio. This here and this here are my extremes. The other two numbers are my means. The cross product property says the product of the means, B times C, equals the product of the extremes, A times D. We can do this because of the cross product property. This should always be true. It's called cross product because you're basically going across the equal sign and multiplying in the shape of an X. So I have a few examples on this slide. If I was trying to solve for a variable here, and I know it's 5 to 6, and 18 to X, I might look at this and say, how would I find X? Well, the cross product property tells me that if I have a proportion, I can do the cross product, and these two are equivalent statements. This causes this. So 5 times X equals 6 times 18. If I wanted to continue solving for X, I would multiply it out and go all the way. However, this is just how I go about solving. At this point, solve for X. Simplify this side, divide both sides by 5, you're done. This top example here is just to show you that the cross product property works. If I have 5 to 6 equal 15 to 18, these are equivalent ratios, first of all, so I know it's true no matter what. I do the cross product, and I find out that I get 90 equals 90. Another true statement. Cross product property works always for proportions. Example 4. So, quite simply, I look at these examples and say, hey, solve for X, solve for my variable. Sometimes it's P, sometimes it's V, sometimes it's Q, whatever it is, I'm solving for it. It doesn't matter what it is, though. Let me copy them down quickly. Alright, now I'm actually really good at proportions. So I was actually very good at looking at this and saying, oh, X is 25. I could look at it and tell, basically because I went, oh, 3 times what equals 15? Well, 3 times 5 is 15, so 5 times 5 is 25. I already knew the answer for X. Same thing over here. Well, 8 is half of 16, so X has to be half of 6. 3. I can do this pretty quickly. But I want you to still practice the cross product for these here, even though they're slightly easier than the other cross products we might have to deal with. Because eventually, you might get to this. Okay, this one's 3 times as large. I can't do that trick here. So practice the cross product property even if it's easier for you. So, cross product, it's a proportion. Good, I can do the cross product. 3 times X equals 5 times 15. Simplify the right side. 3x equals 75. Divide both sides by 3. X equals 25. This one here, 6 times 8 equals 16 times X. 6 times 8 is 48, equals 16x. Divide both sides by 16, x is 3. Again, I said I could do this one in my head, but it's good practice. Because eventually you'll get to one where it's going to be a little bit tougher. 3 times 9p equals 1 times 2p plus 5. Alright, 1 times anything is itself So I made sure to count it here so that way I wouldn't have messed up. But this drops out because 1 times anything is just the anything. I forgot to in parentheses here. So simplify both sides. 3 times 9p is 27p equals 2p plus 5. Subtract 2p from both sides. 25p equals 5. Divide both sides by 25. P equals 5 over 25. Or p is 1/5. Because 5 and 25 are both divisible by 5. Would I have ever guessed 1/5 off the top of my head? Probably not. I would have tried 0, 1, 2, 3, -1, -2, -3, and I would have missed my answer. Because I would not have tried a fraction. You have to do the cross product in cases like this, so it's not bad practice to do it here. Example 2 is, what if I apply a ratio to a problem I know? For instance, what if I know the ratio of 2 side lengths for the triangle are given? And then I say, hey, solve for the variable. Alright, for this example here, I know the ratio of AB, length of segment AB to length of segment BC is 3 to 8. I also know, if I look into the diagram, length of segment AB is P. Length of segment BC is 24. So I also know that this ratio is P to 24. Well, hold on a second. If this side to this side is 3 to 8, and it's also P to 24, it's the same ratio. They have to be equivalent. They're of the same 2 exact lengths. So I really have a proportion here. 3 to 8 is the same as P to 24 in this case. Whoa, no way. So it's a proportion. I know what to solve a proportion. Anytime I'm given a proportion, I can cross multiply. 3 times 24 equals 8 times P. Well, 3 times 24 is 72. 8 times P is 8P. Divide both sides by 8, you get 9 is what P is. And all it's asking for is solve for the variable. I have found P. It's 8. Sorry, it's 9. Whew. So that would be it for today if you are watching day 1. At this point, you should know everything about ratios, everything about proportions. I don't have a whole lot left for the third part of this section. The last part of section 1 deals with the geometric mean. The geometric mean is exactly what it sounds like. For those of you that know what a mean is, it's the average of something. And when we talk about a geometric mean, it's basically the average shape. There's ways to draw numbers like square root of 2 and square root of 3 and square root of 4. And the way we get them geometrically is by drawing certain properties that we see that we'll learn about in this chapter. In a proportion, I get something that is the same length, but I can set up the same or a ratio. So for instance, if I have A to X equals X to B, X is a geometric mean. It's a number that's an average, so to say, in terms of geometric properties, geometric shape. In this case, I might be comparing something like this, where I'm comparing from this vertex to this point here, and from this point to this vertex, that's A and B respectively. And I'm saying A to X is going to be the same as X to B. That ratio is the same. It's a geometric mean. I'm not going into the details about that yet. We'll get there. Don't worry about that part yet. But I get a shape like this, and I say, hey, it's a geometric mean. What is that number? What is its value? What is X if I know A and B? Well, if I do my cross product here, I get X squared equals A times B. And in this case, I get X to be the square root of A and B. This was a number that ancient mathematicians knew they could construct. This is how we can construct the square root of 2. If I made a triangle in this shape, and I made A2 B1, well, x would always be the length that we know as square root of 2. So they could actually find these square roots, geometrically speaking, lengthwise. This is one way that we know the value of the square root of 2, is because they drew shapes like this, and then they measured in terms of decimal how long x is. In this case, x is square root of 2, and they could actually physically measure it out. No way. That's how we got the value of square root of 2? Yeah, geometric. So if I ever ask you to take the geometric mean of two numbers, you multiply the two numbers together, just take the square root. Done. Alright, so I meant that to be not all written out, so let's go straight here. Alright, this says find the geometric mean of two numbers. The first one they want me to do 24 and 48. The second one they want me to do 12 and 27. Now because I'm dealing with radicals, I'm going to do that weird thing where I try to get a number outside of the radical. So if I look here, my geometric mean is going to be x equals the square root of my two numbers, 24 times 48. One thing I can do here is pull out anything I see as a perfect square. Or I could try and match up a number here. For instance, 24 is 24, but 48 here, that's really 24 times 2. 48 is 24 times 2. Okay, makes sense, Mr. H. I get that. I could say 48 or I could say 24 times 2. Same exact number, haven't changed a thing. However, 24 times 24 is 24 squared times 2 tags along. Whoa. Mr. H, you said something before about being able to break up a square root. Yeah, you are able to. So this is really the square root of 24 squared times the square root of 2. Well, the square root of 24 squared is 24. Square 24, then you take the square root. Oh, just undid what I just did. Whew. X equals 24 times the square root of 2. This is how I leave my answer. I can't simplify square root of 2 any further. I'll leave it like this. 2 over here. So the geometric mean equals 12 times 27. This one's a little bit different. 27 isn't like 12 times 2 or anything like that. However, in 12, there's 4. That's a perfect square. So I'm going to break up 12 to be 3 times 4. 27. Oh, 9 goes into 27. That's a perfect square. So I'm going to break this up into 3 times 9. Hold on a second. Let me rearrange these a little bit. This really is 3 squared, 3 times 3, times 4 times 9. Because it's multiplication, I can break up all the parts. So this is the, x equals the square root of 3 squared times the square root of 4 times the square root of 9. So what you're telling me is x is equal to 3 times 2 times 3. 3 square root of 3 squared is 3. Square root of 4 is 2. Square root of 9 is 3. 3 times 2 is 6. 6 times 3 is 18. In this case, you get a positive whole number. And yes, 18 is a geometric mean of 12 and 27. However, if you look at it in terms of algebraic mean, it is not. 18 is only 6 away from 12, but it's 9 away from 27. Whoa. It is a geometric mean, but not an actual algebraic mean. This is how I would do the simplification of a radical. So that way you get nice whole numbers. Basically, you're trying to pull up perfect squares. Sometimes you end up with two numbers multiplying each other, and you take it to be 24 squared or 3 squared. And that's how you pull it out. Other times you'll get a perfect square that you know, like 4, 9, 16, 25, 36, and you can pull it out that way. So, the basic new things here is a ratio. First of all, basically a fraction. Okay, can handle that. I have to be able to simplify a fraction for this part. Cool. Proportion. I take a ratio or a fraction, equal to another ratio or fraction. Oh, okay. And I can solve it by doing the cross product, multiplying the means by the extremes. Whoa. Actually, I think I did it reverse for you. I believe it's means for you this way and extremes this way, but you get the idea. You multiply that diagonal. Okay? And then the last thing is this thing called a geometric mean. It's a special shape formed by triangles, and it's a way that we were able to form like the square root of 2, or the square root of 3, or the square root of 5. Numbers that otherwise would have been very hard for us to form. I think that's all I have for you today. So, at this point, you should be able to do all of Chapter 6, Section 1. You should understand ratios, proportions, and geometric means. We'll cover a little bit more about proportions and how we can use them in everyday life in just a little bit in the next section here. But until then, till next time.